breaking down the walls. So if you're absent, you can watch this video. Hopefully it will help you with the lesson, with the notes. We're going to explore exponential functions. This first example, notice that Joe Patriot is collecting baseball cards, and he currently owns 40. He's going to add 50 new cards each year to the collection. We need to complete this table to explore what is happening in here. So let's go to the table and let's see what's happening in here. So currently he has 40 cards. We can write that that's the initial value. And a year from now, he will have 90, clearly. He's going to add up another 50. You can think of this as being the 40 that he started with, plus 50. We'll come back to the explicit formula later. 2 years from when he started his collection, he would have 140 cards. You can think of this as being 40. And then you have to add up 50 the first year and 50 the second year. 2 50s. 3 years after he started the collection, he will be up to 190. He's got to add up another 50 in here. And you can think of that as the 40 that he started with, plus how many 50s would he be adding? 1 for the first year, 1 for the second year, 1 for the third year. So he will be adding 3 50s in here. So that means that n years from the time he started the collection, you can think of this as he always starts from 40, he adds up 50 repeatedly, and if he's going to wait n years, the number of 50 cards that he will be able to add up to his collection would be n 50s. So we'll come back to the table. I think I'm ready to write down the recursive formula. In order for you to figure out what's happening here, you have to start from 40, that's his starting value. And then to find a term, you have to take the term before and to add up 50. We know that there is a common difference. The value that I'm adding all the time is 50. The difference between these two terms is 50. That means that this is an arithmetic sequence. And we know that again because there is a common difference of 50. Okay, but recursive formulas are very inconvenient. If I want to figure out how many cards he has after 10 years, I'm going to have to figure out how many he has after 9, 8, and so on. So I want to go back and see if I can come up with an explicit formula. The idea, going back to the table, is that if I think carefully about this repeated addition that I had can be modeled as a multiplication. What I mean is that after 3 years, he'll have 40, and he's going to add up 50 times 3 cards. And then after 2 years going back, we'll have 40 plus 50 times 2 cards. And then after 1 year, we'll have 40 plus 50. He's only adding 150. It even works for the first one, in which we would have 40 plus 50 times 0. But the implication in here is that what happens after n years? He started from 40. He continuously added 50s, and he's going to do so n times. That's my explicit formula. That means that the number of cards after n years is 40 plus 50n. So how many cards will we have after 10 years? That's from 40, and he add up 50 10 times. 50 times 10 is 500, so this part here is 500. And Joe would have at that point 540 cards in his collection. Okay, this is an example of sequence, but this is not exponential. This is linear. And the reason it's linear is because it's arithmetic. So this is not actually the type of functions we're going to work into this chapter. We have worked with these linear functions before. Let's now take a look at the next one, in which we will be working with exponential. So Patty is breeding rabbits. She starts with 4. Population triples every year. Let's explore what kind of numbers we have in here with this table. So a year later, after she started, she's going to have 12 rabbits. I think of this as being 4 times 3. 2 years after she started her collection, she's up to 36 rabbits, which is the 4 that she started, and she's tripled her collection twice. The next year, 36 times 3 is 108. You're multiplying by 3 all the time, clearly. And then you can think of that as being 4 times 3 times, because she's going to triple the number of bunnies 3 times. You can see here what is going on. The next one, after 4 years, she's going to have 324 rabbits, which is going to be 4 multiplied by 3 4 times. Repeated multiplication. So, okay. So, the common ratio for her is 3. And what happens here is that the starting value was 4. And to find a term, you have to multiply the term before by 3. That's the reason that this is geometric. There is a common ratio of 3. What's the explicit formula? Well, let's go back to the table. What's another way for me to write repeated multiplication? 3 times 3 times 3. This is the same as 4 times 3 raised to the 4th power. Or in the one before, it would be 4 times 3 raised to the 3rd power. 4 times 3 raised to the 2nd power. 4 times 3 raised to the 1st power. And I want to see how even the first one works. 4 times 3 to the 0 power. 3 to the 0 power is 1, and this is 4, which is the value I was supposed to get. So after n years, it's going to be 4, the starting value, multiplied by 3 repeatedly. How many times? N times. That means that my formula for the explicit will be that the number of rabbits after n years will be 4, which is where you start from, multiplied by 3 to the nth power. Okay, comment, okay? This is not the same as r times 12 to the nth power. That's bad. When you have to do these computations, you have to do exponents, powers first, then multiplication. You will be breaking the order of operations if you do that. So anyway, let's figure out how many rabbits you have after 8 years. She starts from 4. She's going to triple her population 8 times. This is something that you want to do with your calculator because it's pretty big. And if you do it, you're going to have 4 times 3 to the 8th power is going to give you 26,244 rabbits. After 12 years, you would have 4 times 3 raised to the 12th power, which with the calculator would come out to be 2,125,764 rabbits. That's a lot of rabbits. That's an awful lot of rabbits. And now here, they're asking me to figure out what is the average rate of change for the rabbit population. Average rate of change is just a fancy word for the slope. So we want me to figure out what is the slope of this situation. Slope is change on y coordinates divided by change in x coordinates, or change into the dependent variable divided by change into the independent variable. For this problem, it's going to be how many rabbits you had after the 12th year, 2,125,764, minus the rabbits that you got after 8 years, which was 26,244, divided by what? The corresponding values for the years. So 12 years minus 8. If you use a calculator to compute this, you will be getting an answer which is 524,880, and this has units. The units for the top were rabbits, and the units for the bottom were years. So this is as an average during those years from the 8th to the 12th year. She was adding an average of 524,880 rabbits per year. Now, Notice that this is an average. The last year she was actually adding more than that. The first few years she was adding less than that. Okay. Let's now look at our third and last example. Farmer Brown has 2,187 sheep, and every year the population decreases by 1/3. So we're going to complete the table. Get careful in here. There is a tricky part in here. If the population decreases by 1/3, that means that there is still 2/3 of the sheep that are still into the herd. And that means that if you want to figure out how many sheep he has after 1 year, you need to take the 2,187 that he had and multiply that by 2/3. Because remember, what you really care is for how many are remaining into the herd, not how many of them died or he had to get rid of. Okay, so going to the table, what I'm going to have to figure out in here again is how many remaining sheep he has, and into this situation is going to be 2,187 times 2/3, which with a calculator come out to be 1,458. A year later, we're going to have to multiply the 2,187 times 2/3 and then times 2/3 of that again. So if we do that with the calculator, it's going to be down to only 972 sheep. And 3 years after he started, it's going to be 2,187 multiplied by 2/3. How many times? 3 times now. So if we take the 972 and multiply it by 2/3, I'm going to get 648. And I think that we can see what is going on here. I'm not going to do the whole thing for the sheep in here, but I'm ready to write down that the common ratio, the number that I'm using to multiply all the time to get the next term, is equal to 2/3, not 1/3. Careful with that. Recursive formula. Farmer Brown started from 2,187 sheep, and he has to take the number of sheep from the year before, multiply that by 2/3. Okay, how do I come up with an explicit formula for this? Well, you probably know what is coming in here, but let's see. This in here is repeated multiplication. So I could write that as that the number of sheep after 3 years will be what he started from, 2,187, multiplied by 2/3 3 times. After 2 years, he would have had 2,187 multiplied by 2/3 raised to the second power. And in general, I think I'm right to write the formula in here. I would have 2,187 multiplied by 2/3 n times. That's my explicit formula. So I'm going to write it in here. I have that the number of sheep will be equal to 2,187 times 2/3 raised to the nth power. Okay. So how many sheep would have after 8 years? The number of sheep will be equal to 2,187 times 2/3 raised to the 8th power. I'll give you time to do that into your calculator. Make sure you put parentheses around the 2/3, just like I have it in there on the screen. And you're going to get, as a fraction, 256 over 3. As a decimal, that would be 85.333. Now, obviously, that doesn't make any sense. So we're going to say that he would have 85 sheep. What would he have after 15 years is the next question. Well, after 15 years, he's going to have S of 15 would be 2,187 times 2/3 to the 15th power. I'll let you do it with your calculator. and it comes out to be in decimal form 4.994, or what is the same, approximately 5 sheep. It doesn't have that many sheep left. Now to figure out the average rate of change, remember that this is a slope, is going to be m is going to be the number of sheep after 15 years, which was 5, the number of sheep after 8 years, which was 85, divided by years for each of them, which was 15 years to get down to 5 sheep and 8 years to get down to 85. This is going to give you negative 80 over 7, or if you actually do that with a calculator, negative 11.42, and the units for that would be sheep per year. Why is it negative? Because the number of sheep was decreasing. And remember, this average rate of change, that doesn't mean that every year he was losing 11 sheep. That's an average on years 8 through 15. He was losing more sheep the first year, he was losing less sheep the last years. Okay, so let's see if we can summarize everything that we have in here. Let me just go ahead and change colors. Let's see everything that we have in here. So exponential functions can be used to model growth and decay. The rabbit problem is an example of growth, because the number of rabbits is increasing. Whereas the sheep in problem number 3, is an example of a decay. I know nothing is decaying, nothing is stinking, but the number of sheep was decreasing. So decrease, decay, increase in growth. Some vocabulary. These problems are also geometric sequences because the terms have a common ratio. When the terms get larger for exponential growth, the common ratio R is going to be greater than 1. It's also called the growth factor. To say that for these problems, instead of R, usually when we're working in this chapter, we're going to call it B. We're going to say that B is greater than 1. For the rabbit problem, the growth factor was 3. When the numbers get smaller, for exponential decay, the common ratio R is going to be less than 1. It has to be greater than 0. We can also call it like B. B is less than 1 and greater than 0. And this is called the decay factor. And in general, what is going to happen is that the book is going to say that the formulas for this problem are that y is going to be equal to a, which is the starting value, times b raised to the x power. I'll put here the b that way. And b again is going to be the decay or the growth factor, and a is the starting value. And that's it. That's basically what exponential functions are about for our first day.